Two steel arms, each one longer than 2 football pitches, are parked on the banks of the busiest shipping lane into Europe. They have been sitting there, doing nothing, for most of 30 years. That is not a fault. That is the entire design. Because this is the machine's problem, and it is a genuinely impossible one. Rotterdam has to stay open, because tens of thousands of ships a year reach Europe's largest port through this one channel. And Rotterdam has to stay shut, because the open North Sea is right there, and the land behind it is below the waterline. You cannot wall off a river, you need ships to sail up. You cannot leave it open when the sea comes for you. The Dutch know exactly what the second half of that sentence costs. On the night of the 31st of January 1953, a North Sea storm surge pushed straight through the sea defences of the southwest Netherlands. 1,836 people died. It remains the deciding event in Dutch engineering history. So here is what they built instead of a wall. When a surge is forecast, 2 hollow steel gates float out from the banks under their own buoyancy. They swing across the channel until they meet in the middle. Then they take on water, get heavy, and sink onto a concrete sill on the riverbed. The river is closed. When the sea drops, they pump themselves dry, lift off, and swing back out of the way. And nobody signs off on any of it. There is no engineer with a hand hovering over a switch, no minister to wake up, no phone call. A computer watches the forecast, and when the number crosses the line, the computer closes Rotterdam. Hold on to that, because the interesting part is not that they built it that way. It is what happened the first time it was true. This is the Maeslantkering, the Maesland Barrier, at Hoek van Holland, where the Nieuwe Waterweg meets the sea. It is the last piece of the Delta Works, the flood defense program 1953 started, and it was commissioned on the 10th of May 1997. Rijkswaterstaat, the agency that runs it, makes one careful claim about it. No other flood barrier in the world has larger moving parts. More than a quarter of the Netherlands sits below sea level. This is a delta, a country assembled out of river mouths, pumped dry polders and dikes, where the ground behind the defences is lower than the water in front of them. There is no high ground to retreat to. Whatever holds, has to hold here. Which is why the Dutch do not design for the worst storm on record. For the most densely populated part of the country, the standard is a flood with a 1 in 10,000 chance of happening in any given year. Not a century, 10,000 years. That is the number the whole machine is built to satisfy. Every simpler answer breaks on the shipping. A dam closes the channel permanently and strangles the port. A lock works, but every ship has to stop, wait, and be cycled through, and on a channel this busy, that is the same as closing it. A lifting bridge span tall enough to clear the largest ships would have to stand higher than almost anything ever built over water. The channel is 360 meters wide. Nothing conventional spans that and still gets out of the way. So they built something that does. The first thing to understand is that each gate is not a door. It is a hollow steel box 210 meters long and 22 meters tall, and it floats. It is built and maintained in a dry dock on the bank, and it spends its life sitting in that dock in the dry. A gate that floats needs no cranes, no jacks, and no rails to move 210 meters of steel. The water it is fighting is what carries it. And that creates the hardest problem in the whole design. A floating gate does not travel in a flat line. It pitches, it rolls, it rides the swell, while a storm is hitting it, and all of that has to pass through a single connection into the concrete on the bank. That connection is a steel ball joint 10 meters across, weighing 680 tons, cast and machined in the Czech Republic by Skoda. It lets the arm move in every direction at once. Get it wrong, and the arm binds mid-swing with a surge behind it. It is widely described as the largest ball joint ever built, a claim worth attributing to popular accounts rather than to Rijkswaterstaat, which does not make it. Each gate is held by a lattice truss arm 237 meters long, not a solid beam. A lattice because a solid beam that length would spend most of its strength carrying its own weight. Open the 2 arms and gates together, span roughly 420 meters, and leave the full 360-meter channel clear. Each complete arm assembly weighs about 6,800 tons. And every one of those tons moves on the water. Meeting in the middle is not closing. A floating gate is still floating, and water goes straight under it. So valves open and the hollow gates flood, deliberately, until they are heavy enough to stop floating and settle onto the sill. That is the 90 minutes that matters. About half an hour to swing the gates into position, about 90 more to ballast them down. The half of this machine nobody photographs is on the riverbed. The gates seal against a concrete sill laid across the bottom of the channel, and a sill in a working shipping lane silts up. If sediment is sitting on it when the gates come down, the gates do not seal, they rest on the sediment. So the sill gets surveyed and swept. The most advanced part of the barrier depends on the riverbed being clean. And here is the constraint nobody expects. Closed, this barrier is holding back a river that keeps arriving from behind. The Rhine and the Maas do not stop for a storm. Water piles up on the inside while the sea is held on the outside, so a closure is not a wall you leave up. It is a gap you cover until the sea drops far enough to open the gates and let the river out. Which is why the call is not a judgment, it is arithmetic. The decision system takes the water level forecasts and applies a threshold, 3 meters above the Dutch sea level datum at Rotterdam, or 2.9 at Dordrecht. Either one is enough. It runs unattended, it issues the closure order, and no human signature is required anywhere in the sequence. Which moves the entire safety case into software. This is a system that must work correctly on a day it has never seen, having spent years doing nothing. So the software was specified formally and verified against that specification rather than simply tested, because you cannot get useful test coverage of an event that has happened 3 times in 30 years. The barrier's real failure mode was never the steel. Which leaves one honest way to know: run it anyway. Once every year before the storm season opens, Rijkswaterstaat closes the Maeslantkering barrier on a calm day for no reason at all. Ships are held, the arms swing, the gates flood and sit down on the sill, and then the whole thing is reversed. They rehearse the catastrophe in flat sunshine, because the alternative is finding out during one. And what is behind it is not a picture of a city. It is the largest port in Europe, running at full rate, container terminals, tank farms, the refineries that feed a continent's fuel, and the low, dense, drained heart of the Dutch delta immediately behind that. So it is worth being precise about what failure would mean, and about the fact that it has not happened. If the gates were ordered shut and one arm did not arrive, the surge would not meet a wall. It would meet a half-closed channel, and a narrowed gap accelerates water rather than stopping it. The barrier would be aiming the surge up the river instead of blocking it. That is the scenario the annual test exists to make impossible, and everything you are seeing here is a simulation. Which brings us back to the loop. The Maeslantkering barrier has closed against a real storm surge 3 times. The 8th of November 2007, the 3rd of January 2018, and the 21st of December 2023. But there is something inside those 3 dates. For 2007 and 2018, Rijkswaterstaat had lowered the trigger beforehand, from 3 meters down to 2.6, specifically so the machine would be forced to fire and they could watch it do it. For 16 years, humans quietly moved the goalposts to see whether it worked. In December 2023, nobody touched anything. The surge crossed the real design threshold on its own, the computer issued the order, and Rotterdam was closed for about 8.5 hours. It worked. No signature anywhere on it. Except that the number the whole machine is arithmetic around is a number about the sea, and the sea is moving. A 3-meter threshold means one thing at 1997 sea level and a different thing at 2100 sea level. The same barrier closes more often, holds against more, and gets less of a window to let the river out. Dutch water safety planning treats how far that can be pushed as an open question, not a settled one. This is flagged here as a live question, not a finding. Which is why engineers keep coming to look at it. London has run the Thames Barrier since 1982 and closes it far more often now than it was designed for. Venice finally has its mobile gates and is learning what it costs to lift them for every high tide. Every city on this list is doing the same arithmetic the Dutch did, and finding, as the Dutch did, that a barrier is not a solution so much as a schedule. But on a bright, ordinary Tuesday, the Maeslandt barrier is a wide, empty, quiet piece of white steel with cyclists on the dike beside it and ships going past it. It is not standing guard, it is parked. And the only reason anyone can treat it as scenery is that the machine has already decided, without asking, what it will do on the day it stops being scenery. If you want more mega projects taken apart like this, subscribe. There's a new one every week.